So this is the patch that we'll be using as a reference. Not too complicated, but not too simple. Okay, so basically trial and error and no sequencer. We are going to translate this to Csound. Now let's go into Csound here, colors. Okay, so what is the name of this? Temp. Okay, this is a patch called temp. Maybe you should call it fake sequence or not a sequence. Maybe I'll call it that. Not a sequence. Okay, good luck with composition, not a sequence. Orchestra. Okay, let me just open this score. So this is a script that I've made that creates these files. So okay, first thing you do is detune VCO. That's a easy thing. Detune VCO for 40.1 and okay, so the mixer, so we are going to just add it and let's see if we don't want to divide it, just add it. Might be slightly loud, but let's just see if this works. Okay, yeah, you can hear this detune thing, so it's working. By the way, how much is it getting detuned? 261.63 to 61.53, so that's 0.1. Now we have frequency modulation that's happening by, and it says 9%. So we're going to go by year. We're going to see how it's. So one way to do it is take this mix and let's hear this mix alone. That's loud. Okay, so we got an idea of almost like an octave, but little less than an octave. So we're going to try that. Okay, modulate, control frequency, not audio. So we want K0. LFO has parameters as amplitude and frequency, which is 1.5. okay, so obviously if you're going to do it here, it's not good, right? We want it here. We want it to be used here. So let's just take this guy above, and now we have a, so this guy is going to go up and down from -1 to 1. Oh, actually, let's hear this, right? If we do this, what do you think will happen? K0 width is just 1, so this is going to be barely audible. Let's just see. Yeah. You can almost hear it. It's a very slight vibrato. Now we want this to be at least, okay, trial and error, 100. Actually, you could do it like this as well. So this is the width of the LFO. Right? That sounds good. So we got a detuned VCO, which is frequency modded to an LFO. Okay, now what do we do? If we go down this route, ADSR, then we will need a trigger. We need to trigger this with a low frequency oscillator. Instead of that, let's introduce Csound's most powerful device, which is called tables. You can think of this as a sequence of numbers, basically an array. So say your LFO, if you are already familiar with wavetables, then you know what this is about. But if you're not, it just means that this is going to be an array and it's going to run it's going to be played. So suppose you want a triangle wave. You make something like this. These are discrete values. So once again, everything is from -1 to 1. So you just have to set up a table with this, and this thing is going to cycle. It's going to cycle through repeatedly. It's going to scan through this table repeatedly at some frequency. Now this, in Csound, this is called F table. So I'm going to draw a table and then we'll implement this. It's going to be something like, it's going to be unipolar because it's going to look like a pulse, and it's going to have, so this is basically silence. This whole part, this is silence, and this is the envelope. Right, let's take something like 1024. It could be anything, and so we wanted a PWM of 4%, 4 point something percent, which means 0.04. How much is 4% of 1000? 45. So this is going to be 45. We could probably make it something like 64. Let's make this 64. Why am I taking, so okay, so we are restricted. This has to be a power of 2. It has to be some integer power of 2. Okay, and this can be anything. So we could do something like 16 this width is 16, this is also 16, and inside 32, or 36, something that is comparable with 4.5% PW. We're going to make this table. Okay, now how do you make a wave table in Csound? Do it like this. F2, so we can say this is the table ID, we can call it. So you see, it's got everything. There's a F table for everything almost. Okay, there's a lot of stuff. What we're going to take is composite waveforms. No, we want something line. Yes, exponential. No, straight line. Gen 7 is what we want, right? Construct functions from segments of straight lines. So F table ID, let's just write that down. What is the 0 thing? Oh, time. Yeah, so time is basically it's always 0 for table because this is a declaration. Size, this is the gen and this is the args. So 0 size is 1024. Gen 7. Okay, A, N1, B, N2, C. So this is 0. So A is this guy, A0. This is 16. So 0, 16, highest point is 1. And then gap is 32. Again 1. Then gap is 16, 0. This is the sequence that will build this trapezium. Okay, and then what is this? 1024 minus 64. This is 1024 minus 64, right? And it's all just 0. Actually, we could just leave it as it is. Let's type this in. Okay, 0, 16, 1, 32, 1, 32, 1, 16, 0. And let's see what happens. We'll not write any code for this. We just table, or let's say wave table acting as PWM envelope. We just want to see if the ASCII waveform gets generated. Do you see this? So it looks like a blip here. Hold on, let me just make this I'm enabling displays for the time being so that you can see. So you look at this looks like a trapezium, right? And there's a whole lot of silence. So this is what it is. It's a trapezium, and let's make it a little. So supposing you did 1024 minus 64 and then 0, this will give you the same effect. So if you don't give anything, it's going to assume that there's nothing. See, it's the same. Slight convenience. So this is going to be our table, and table number 1 is already set up as a sine wave. We don't really need that sine wave, but my script builds this automatically, so we could even get rid of this. Let's say we don't need this. We could make this the first table, right? And let me call this as the score table. Semicolon is comment in Csound. Yeah, args ... because you can have each gen routine has its own arguments. And what was I doing here? So what we have done now, we have a table now, okay, and we are going to run it like a wave, like an oscillator. So we're going to use the oscillator opcode. Let's call it envelope, because oscillator oscil is an opcode. Okay, it's a, we want just oscil, simple oscillator. So this is actually a wavetable oscillator. Okay, it reads a table. So in the beginning when I read this, I had no clue what was being said. Now I understand, because without knowing what tables are, it's just Greek and Latin. It's basically a wavetable. Amplitude is 1 and frequency is the frequency of our LFO here, which is 6, right? So we actually don't need this square PWM. So all of this we can just get rid of it. Okay, and the third parameter is what is the most important. What they refer to as IFN. IFN is the number of your function table. In this case it's 1. So this is a wavetable that's going to simulate a curve like this. It's a trapezium type of curve. We're going to just multiply this. So now it makes stuff, it makes everything slightly mathematical. So now actually you could even do this here, k and v into k1 into k. So k1 is now we don't need, it doesn't exist. So we have k and v into a01. So a bit anticlimactic, see what we are doing is there's already a waveform, the detuned wave, okay, and that's audio rate. That's basically your sawtooth, and that's constant volume. We are multiplying this with this envelope, okay, we are multiplying it, so you will get the waveform shaped by this trapezium like thing, okay, and the second period will be this coming back again. So we should get something like a pulse. Let's just see. Right, if you can hear that. Let's try changing this waveform, okay, we'll make something actually you can craft a waveform that that doesn't even need a delay. Okay, so I'm going to make something like this, okay. So also, if you get creative, if you make this rapid enough, you can change the timbre of the sound. So let me put 16, how much will this be? 32, 8. This is again 32 and 8. Let's just try this. So we don't have to change the existing one, just use new tables and change the table number in the orchestra file. So 0, 16, 32, 8, 32, 8. Oh, sorry. 0, 16, 1, 32, 1, 8. Let's make it 0.5. What I mean by that is this point is half. This is half. So it's basically an amplitude versus time. And then we go 32 again and then 0. What? No, 0, 16, 1, 32, 1, 8, 0.5, 32, 0.5, 8, 0. Cooking up values for F tables is art in itself. Now I've made it like not too creative, but just so that we can notice the effect. So I'm going to change this table number and that's it. Now you see how powerful this is. We got something much more powerful than ADSR, because this is basically, it's not just attack and decay. You can have attack 1, decay 1, attack 2, decay 2, so on and so forth, as many as you want. So let's run it and see what. Okay. So doesn't sound too creative, right? So let me make a few changes here. Because what I want to do is, you see, there is a delay in VCVRack. There's a delay module. I want to get similar effect without delay. So we want something like this, and then how about this? So let's say this is 1, this is 0.5. okay, so this is 0.5 and this is 1, and so let's cook up some numbers for these trapezium, right? So 0 is, let's start with 0 x time gap is 16 samples, it reaches 1, and then 32 samples, it is still at 1, and then 16 samples, it reaches 0. All right, we are now here. 16, 32, 16. Now how much do we put? Shall we put this as 32? So let's put this as, or let's put it a little bigger, right? These are samples, not this is not time. Yeah, this is time units, but these are counted in samples. So let's keep some slightly bigger, 64, and then the whole thing repeats. This whole thing repeats, but instead of 1 we'll have 0.5. So 64, 0, 0, 64, 0, gap is 16 and reaches 1, gap is 32. Oh sorry, not 1. This is going to be not 1. Zero 16.5, 32.5, and then 16 and 0. If you lose the thread of attention, you'll have to start from this picture. So always have this image of this graph in mind, otherwise it's very hard to look at these numbers and imagine. Usually if I lose track, I just start over again. So I'm going to type this into another table. So now that, let me make this a little shorter so that I don't have to resize. 0, size is 1, 2, 4, 7, 0, 16, 1, 32, 1, 16, 0. Zero 16 1 32 1 16 0 64 0 16.5, 32.5, oh dear, 0.5, 32.5, 16, 0. Okay, let's look at this full screen. 0, 16, 1, 1, 0, 0, 0.5, 0.5, 0. So we have table 3 that is going to mimic a delay. So we're going to adjust this 64. It may be too small a number, so it might not even register, might not even sound like a delay. So we're going to use table 3. Now you see we just changed the number and we've got, okay, it's too, wait, where is the, oh right, yeah. Looks like it changed the timbre, but I can't make it out. It doesn't really sound like a delay. So let's make this something bigger. Okay, 64, let's say, how about 512? That should sound more substantially big. Oh yes. Okay, so not maybe 512 is too much, but you see it's very sensitive. So these are so now you might imagine converting from VCVRack to Csound. Even if we are unsuccessful in getting the exact Csound VCVRack patch, we inevitably learn something new. So that was the idea behind cross-pollinating patches. So let's keep it at maybe 192, and or probably even more fun, right? Let's just copy this and create another one and add another section of silence, 0, 128, and copy this whole section. .25. Now what am I trying to achieve here? So the idea is, delays, they don't linearly decrease, they decrease exponentially, they decrease almost logarithmically. So let's see. Okay, if you look at fourth one, so these are pulses, but they're really close. And so this is a wavetable. This is how you make a, so basically what I did in the fourth waveform was create I made this 128, and then I made a smaller, God, is it not this? Oh dear. Yeah, I made a smaller trapezium here. So you could do stuff, you could draw all kinds of stuff here. Drawing with numbers basically, and just multiply it to the output and you'll get so suppose you wanted more attack, right? You could let's say we'll use the first one only, and we'll change this to not 16, but we'll not reach 1 so fast. We'll, let's say 64 and 64. This is going to sound slightly different. Okay, now slightly different, maybe not that pronounced, but let's make it 128. Now it's going to be definitely pronounced. Make this 16. So this sort of stuff. So this is okay, so this is unipolar wavetables. So it's all going from 0 to 1, and we are making it behave like ADSR envelope, but this is not really an ADSR. This is it has the power of a wavetable. It's a wavetable envelope. Okay, anything else? Okay, so delay. Oh, we also have a VCF, by the way. Mixers going into VCF, right? And low pass of that is going into your output. Okay, this can be done easily. Let's just make low pass filter. What is the cutoff? 737, and it has resonance. So there's a lot of low pass stuff. If you search for low pass 2, there's actually Moog VCF, but we'll use the simplest. Let's go to BotLP, Butterworth low pass, right? Asig K-Freak, simplest. So we will make this not equal to but LP, and this is a signal, input signal. K-Freak is basically this guy's cutoff. Why is it K-Freak? And so you'll notice this K-Freak versus A-Freak. It basically means if it's a control signal or an audio signal. Just put 800 here and run it. Okay, now you see the volume has audibly decreased. So that's a VCF. Well, actually not a VCF. So Butterworth, what is this? This Butterworth is basically a algorithm or a recurrent. It is a kind of filter design. I'm guessing FIR. It'll have some recurrent relation which we don't have to worry about right now. So, and at the end, what if we want to add some delay? Okay, so ADLY delay. So there's actually delay is again a rabbit hole, it's a set of rabbit holes. So we are not going to go into tapping variable delays and all that, but there's a whole lot of stuff that you can do with this, but we want to do just a simple delay just for now. A sig and ITLT. A sig is 01. Okay, so just take the delay time 0.26. Now you notice it's not going to sound like the VCVRack delay for now, okay, because this is a, I guess this is a convolution delay 0.26, whereas in our case it's a simple delay 0.26. Mix, okay, mix, we don't have any mix. We're just going to what we'll do is, let's see if we can, okay, now we don't want to have the KNV here. We are going to restructure this and say this is A2, this is going to be A1, maths expressions, right? And let's remove this. A2 is the filtered, so we want delay. So the signal path is from right to left, okay? And we want to do ADLY plus A2. Why? Because this ADLY is actually the wet signal. So if you don't give anything, straight, okay, you just give ADLY, then now you might not have noticed, but there's a gap in the beginning. See that silence at the beginning? That's because it's just delayed. This is the 100% wet signal. So we want to add this to the dry and get a mix. For now 50%, we can so now you can decide how much mix you want. So let's say mix was 21%, so 0.21 into ADLY. See what that sounds like. Okay, so and how does the VCVRack one sound? Oh, okay, I guess did we change something? Maybe, oh okay, maybe this is 1.8. Okay, so skeleton is similar, but why we get different values is because of this. So the LFO width 9%, I'm guessing VCVRack percentages, they are multiplicative. So this LFO width is some function of your input signal, whereas in this case we'll have to tune it. Let's see if 50, maybe it is. So you could actually make it you could say something like 440 into 1 plus K0. Okay, and make K0 percentage, right? So 9% is what? 0.09 into K0 and make this 1. So all kinds of weird math calculations. You could do something like this to get the exact stuff, but we don't want to do that. Let's just see what happens. So why am I doing 1 plus? Because in multiplication we need a bipolar signal, right? So lowest value of K0 is -1, which will become 1 plus 0.09 into -1 is 1 minus 0.09, and max is 0.09. So 0.91 lowest value and 1.09 highest value. So you multiply 440 into both sides of, so God, this is more complicated than, yeah. So lower end you will get this, and higher end you will get 479. So you could do this. I mean, from now it's like a matter of taste what you do with this, but let's see if this gets us. Oh, that's odd. Oh, now we made it a function of frequency, right? Oh, I get it. Yeah, frequencies are 261. Okay, so let's make it 261 point, was it 261.63, 261.53, 261.53 and 261.63. Okay, that still doesn't sound like it. It's clearly going a little higher. Oh, right, our LFOs are offset. No, that's correct. It's bipolar. And this is 9% frequency modulation. Okay, so what is the equivalent that we'll have to, let's try with something. Okay, 1 plus 0.18. We could make this another function. Let's see if this. Wow, this is, so now it looks like VCVRack is not doing this. So it doesn't matter, you just yeah, modulate to taste. This sounds closer. What if I play this and this together? So let's change something here. Let's make it 0.6, right? So 16 into, okay, let's make it 0.4. How is it going to sound now? What? Why is, oh, that was a little, yeah, it was a little too slow. Maybe I was, all right, 1.6. Okay, that's the same. 1.9. If it's not a perfect, so this will keep changing now. So this sort of stuff, try with another table. So you see, what if we put the last one? Okay, this is definitely changing the timbre. So I think, yeah, that's it. So we ended up not using ADSR, and we got it from the table itself. I will introduce exponential gen routines in another video. All right, that's it.